Hello, everyone. Welcome back to another Flan Talk. Today, we're excited to have Dana to give a talk. Dana needs no introduction, but for the people who don't know her, she is a former faculty at Yale, and she's been a cornerstone of our online community as well. She's done some very interesting work trying to understand transformers from a formal perspective, and in previous works, which she may also be known for, she's done very influential work on machine learning, computational learning, and some of you may know the L-star algorithm, which she was responsible for. So we're very excited to have Dana tell us a little about Transformers today. And thanks, Dana, and take it off.
Thanks very much for the opportunity to give this talk. Um, it was originally designed for a technical but not necessarily familiar with Transformers audience. So there'll be some slides that are not necessarily relevant to this audience, except to see how I present that kind of thing. It's based on work I've done with a variety of other wonderful collaborators, David Chang, Bob Frank, Sophie Howe, Will Merrill, John Roski, Ashish Sabharwal, Lena Strobel, Gail Weiss, and Andy Yang. So we'll start with things that you're probably familiar with. Why should we try to understand transformers? Well, there are various opinions about what will happen with large language models and their ilk, generative models in general, which at the moment are largely based on a transformer architecture. Two of the poles of the argument are represented by these two books. Yudkowsky and Soares argue that uh, if indeed we succeed as the human race in building general artificial general intelligence or artificial superintelligence, that the values embodied in such a thing would be so alien to humans that advertently or inadvertently it would just cause our extinction. And therefore, what we should do as a species is stop all advanced AI research until we actually figure out how to control it properly, which doesn't seem to be too likely to happen at this point. The other book by Bender and Hanna takes a very different view and argues that things like artificial general intelligence and artificial superintelligence are in effect a smokescreen for the usual specter of capitalists behaving badly. And if we pay attention to those things, we improperly ignore the actual harms being caused by that capitalist activity right now. And of course, there are positions in the middle. So Aschenbrenner's vision is that we're, very near to getting artificial general and shortly after artificial superintelligence, and that it should be, from a sort of nationalistic point of view, nationalized by the US to ensure military superiority. So there are a lot of opinions about the future of this technology, but we really don't understand it too well, and we probably should. This is the diagram, of course, from the famous original paper on transformers that you've all seen reproduced in many papers. It's got, in orange, it's got attention units, layers, and in blue, it's got feed-forward layers, and it's got a variety of things to patch them together. The piece on the left, this piece, is the encoder. The input comes in, and this was originally designed for a natural language translation task. So the input was a a sentence in the natural language that's embedded as a sequence of vectors processed by a sequence of layers like this in the encoder, which eventually produces something which is decoded into the other language. So the intention is that the meaning of the sentence, its correct translation, will be produced in the outputs. As an example of how attention might be relevant to a task like translation, we can think about translating the English sentence, "the quick brown fox jumps over the lazy dog," into French. So the encoder, in effect, reads the entire sentence and kind of figures out the parts of it and is thinking about how they fit together in some metaphorical sense. And then the decoder begins to produce the French sentence on the right. So in order to produce the first word, le, it needs to attend to, in the English sentence, the first word of the English sentence, the. It's a definite article, but it also needs to attend to the noun that's going to be the subject of that article in order to get the gender correct. So it's paying attention to the and fox, in effect. To get the word fox, renard in French, it needs to pay attention to fox. It needs to pay attention to brown to produce the brown. When it gets to brown, it could be paying attention to brown and fox here, or it could be paying attention to the words it's already produced. So renard, and we get the gender right for brown. So this is kind of a sense of what attention was doing in the context of this natural language translation task. So this is a fascinating, so the subject of transformers is a kind of fascinating topic in the history of science. And we can observe the theoretical and practical developments kind of happening in parallel here. So this was, early years here. On the left are orange circles that show the relative number of parameters of these models from OpenAI. So GPT-1 is this little orange dot, and GPT-2 got a bit bigger, and GPT 3.5 got bigger. Down the middle, we have years, and here we have some of the early developments in the theoretical study of transformers. Of course, OpenAI stopped telling us how many parameters were in their models about then. So we have, we can only estimate these things. So what is it? What does the orange circle look like this year? Well, it's kind of like this, maybe, since we don't really know the numbers. And going on into the future, this is a picture from the New York Times of a development with OpenAI and SoftBank and somebody else that's intended to house the hardware necessary for large language models. These little ant-like creatures here are automobiles. So if we look at this picture, I want to get the statistics right here. So it was OpenAI, SoftBank, and Oracle in Abilene, Texas this year. The total area is 875 acres. Its power requirement is 1.2 gigawatts. So if I'm calculating correctly, 1,000 of these would need essentially all of the current electricity generating capacity of the US. So it's not going to scale too many more times above this. further order of magnitude increases are constrained by power and also land. Land is not quite as dire, so the total land area of the United States would accommodate about 2 million of these things. So what I have here is my my kind of interaction with GPT-2. So the second of the little orange disks. So when GPT-2 was exposed to the general audience, it was not a chatbot, it was a prompt and receive, a completion operation. It was offered as talktotransformers.com. And I began to play with it and decided that it was quite astonishing. So this is a quote from the GPT-2 paper. The top text is the context or the prompt that was provided by a human being. So in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. And then there's a completion by GPT-2 that goes on about the scientists named the population after their distinctive horn, Ovid's unicorn, the four horns, silver, white unicorns. I don't know how suddenly unicorns have four horns, but the coherence, I mean, this looks ridiculously primitive compared to what the current language models can do. But at the time, it was just stunningly coherent, syntactically correct, maintaining the subject from paragraph to paragraph and so on. I've highlighted in green there that it happened to just pick Jorge Perez's name as one of the theoreticians that was worried about transformers. At the time, I was astonished at what these things could do. And I felt like I should run around the campus. So this was 2019. I should run around the campus warning everybody about what was coming. Of course, by now they don't need the warning. So we'll talk a bit about the theoretical development in studying transformers. This is the notion of the contrast of expressivity and trainability. So in expressivity, we're asking basically an existence question. If we had ideal parameters for this model of transformer, could it perform the task? And trainability, which is of course the more salient thing for actual applications, is can a transformer be trained to perform the task? Typically, the question regards a variant of gradient descent. There aren't too many theoretical results about the trainability. It's not only do the parameters have to exist, but this particular algorithm that you're thinking about has to be able to get to it in some reasonable amount of time. So for the rest of the talk, we'll be talking about expressivity. Perhaps the earliest theoretical result on expressivity was this paper of Perez et al. On the Turing completeness of modern neural network architectures. Well, modern in this case meant the transformer architecture and the neural GPU architecture. Now, probably you're not too familiar with the neural GPU architecture, and since that time, the transformers sort of absorbed all the attention. There was this issue of modeling a discrete behavior, namely the behavior of Turing machines, with a model whose natural dwelling place is continuous. And the answer for that was average heart attention. We'll talk some more about attention. And they needed some position encodings, and they gave a step-by-step simulation of a Turing machine. So each step of the machine was another application of the decoder unit. So it would produce one step, which was recorded in a log that had the current state, the current symbol, and the direction. And this sequence grew longer and longer, step by step, with the simulation. I've always thought that autoregression sounded like something that belonged in the Diagnostic and Statistical Manual of Mental Disorders. But anyway, so let's look at this soft versus hard attention question. So what happens is a position pays attention to other positions, and each position gets a score of indicating how much it should be paid attention to. So we imagine in the table, we have the scores for one position called I for 5 positions, 1 through 5. So we go from 0.7 down to minus 0.6. In soft attention, each of those numbers is exponentiated and then divided by the sum of the exponentials. So in soft attention, all of the positions get positive attention. So the green bar is full attention. These are, in effect, probabilities because we've normalized by the sum. And even 4, which has a negative score, gets positive attention in soft attention. However, in average heart attention, what we do is we look through the scores and find the maximum, which is 0.7. And then all those positions that have the maximum score get equal attention, and all the other positions that miss the maximum get 0 attention. So over here we have a picture of average heart attention. So 2 and 5 have the maximum score, and each gets attention 0.5. Obviously, if there's just one position with the maximum attention, it gets full attention and everything else gets 0 attention, which is useful for doing things like copying. So what can transformers not do? So sorry, I was going to say something about this. If we look back at the Perez result, it says they're computation universal. They can do anything a Turing machine can do. They can compute anything computable. So it's there's nothing they can't do that we could imagine computing by some other means. But in fact, to understand the capability of transformers, it's useful to look at the transformer without the context of autoregression. So that's what we'll do here. We go back to the transformer model, and we remove the decoder portion and route the output of the encoder directly to the output interpretation. So this is the encoder only model of the transformer. We don't repeatedly apply it. We can't simulate step by step by looking at what we just did. What happens is the input comes in, the finite number of layers of attention and feed forward are applied, and you get an output, no further activity. So this is sort of going back to the non-chain of thought version of a transformer and asking what it can do. So a very early and influential paper on this was Michael Hahn's Theoretical Limitations of Self-Attention in Neural Sequence Models. And he proved some fairly definite negative results for this case. So if we think about transformer encoders, so we don't have autoregression, they cannot recognize the fairly important formal languages of even parity strings or strings of balanced parentheses. And they can't do it if they have unique hard attention or soft attention. So this was kind of a very devastating set of negative results. If we look at Hahn's abstract, he says these limitations seem surprising given the practical success of self-attention and the prominent role assigned to hierarchical structure in linguistics, suggesting that natural language can be approximated well with models that are too weak for the formal languages typically assumed in theoretical linguistics. Well, of course, linguists are quite aware of the fact that humans can only deal with a certain amount of center embedding before they stop being able to keep track of what's happening between the beginning and the end. So this is really the age-old issue of how can we make a model that's mathematically tractable, but still accurate enough to the phenomena that we get insight. So I would argue that no, we don't need to throw away the linguistic model. Hahn's proof for the case of hard attention and parity was, first of all, for leftmost hard attention. So this is not average hard attention. It basically says if there are ties in the attention mechanism, so several positions that get maximum attention, then what I will do is I will pick out one of them, say the leftmost, and give that my full attention, and everything else gets zero attention. So it's a hard attention, but it's not exactly average hard attention. And the proof that he used random restrictions, which was very much based on the techniques in the proof that parity is not in the complexity class AC0 by first, Sachs, and Sipser. So parity circuits in the polynomial time hierarchy gave this random restriction proof that parity is not an AC0. And I had a lot of trouble understanding Michael's proof and began to wonder if we could just use the first Sachs and Sipser result rather than the proof technique, which turned out to be possible. So with my colleagues, Sophie Howe and Bob Frank, we found that all the formal languages that we could recognize with leftmost hard attention, transformer encoders, are in fact in the circuit class AC0. Well, what's AC0? AC0 is finite depth, unbounded fan-in Boolean circuits. So your ors and ands can have arbitrarily large fan-in, but the depth of the circuit, so the length of the path from the input to the output is bounded above by some constant. So this has a corollary that it's contained in this complexity class, that these transformers can't recognize parity or balanced parentheses or majority or anything else that you can prove is not in the circuit class AC0. And the proof was a direct and non-uniform construction of a circuit family given a transformer encoder. So you have the transformer encoder and you turn it in to a sequence of circuits, one for each length of the input, and you show that that circuit family is constant depth and polynomial size. But this is in some sense a very weak result because leftmost hard attention is a kind of weak notion. And AC0 is a pretty low complexity class. and it can't do things like arithmetic and counting and so on. For example, it can't do parity. But Merrill and Saberwall and others following on said, oh, yeah, that's the wrong circuit class to be thinking about. Let's think about TC0. TC0 is constant depth, so that you reflect the constant number of layers of the transformer, but it allows threshold gates in addition to and or not. And a threshold gate just takes its inputs and outputs 1 if a majority of them are 1, and outputs 0 if a majority of them are not 1. So the addition of threshold circuits adds, in effect, the capability of arithmetic. And what Merrill and Saberwall started out showing, the first line, they were looking at average hard attention and precision of the numbers in the activations was log n bits, and it was non-uniform, that first result. And that gradually got improved. So there's two kinds of results here. There's for average hard attention and soft attention. There's potential restrictions on the precision of numbers in the activations, and there's how much uniformity you manage to achieve. So uniformity is a notion of how much computing power you need to turn the transformer model you're talking about into a circuit. So we've moved on from leftmost hard attention to proving upper bounds on the capability of average hard and also of soft attention. So going down the chart, this is a chart that comes from David Chang's recent paper. Going down, we get we can accommodate more and more precision, and we get more and more uniform constructions. So at the bottom here, we're looking at average hard attention. At this point, no limit on the precision, and the uniformity of the resulting construction is best possible. For soft attention, we're assuming the precision of numbers is bounded above by a polynomial in the length of the input, and we get the best possible uniformity in this chart. A brief interlude on TC0. So, as I said, we get arithmetic, integer addition, subtraction, multiplication, division. We also get sorting balanced parentheses of any number of types. So we know that AC0 is strictly weaker than TC0. These are the two complexity classes I've been talking about. TC0 is contained in NC1, which is log depth Boolean circuits, which is contained in L, which is log space, which is contained in P. Now, this being complexity theory, these inclusions are not known to be proper, which is, after 50 years or so, you would hope for more, but well, anyway. So what we have is, because transformer encoders are contained in this class, and we think these classes are bigger, problems that are complete for these larger classes are not likely to be computable by transformer encoders. And some of those complete problems are down here: true Boolean formulas, the word problem for the set of permutations of 5 things, undirected graph connectivity, systems of linear inequalities, universal context-free grammar recognition, which means you're given the grammar as well as the string to parse. So those are negative results, things that can't be done, upper bounds. But what can they do? So one of the most significant and influential papers in what they can do is this paper, Thinking Like Transformers, so Weiss et al. They introduced a language called RASP, or Restricted Access Sequence Programs. And the idea was that the operations that are natural in RASP are operations that are easily implemented in transformer encoders, so that by writing RASP programs, you could demonstrate that something could be computed by a transformer encoder. The data types they consider in this language are length n sequences, typically of numbers or characters, and n by n Boolean attention matrices. So not, they don't have a full set of operations on matrices, but they have these attention matrices that are meant to capture the attention computation in transformers. The input to such a program is a sequence of tokens and an index sequence, that is the sequence of their position. So you get two sequences to start with, the token sequence and the index sequence. And the operations you can perform are the element-wise operations on sequences. So here I've taken two sequences and added them together element-wise. So this corresponds to the feed-forward layer in a transformer. Select and aggregate together correspond to an attention layer. So select takes two sequences and a predicate and produces an attention matrix. And aggregate takes an attention matrix and a sequence and produces a new sequence. Let me just give you an example. So this is a RASP program to reverse its input sequence. So the input sequence here is RATS. The indices are 0, 1, 2, and 3. This first operation is a select operation that takes the two sequences, the indices and the sequence of length minus indices minus 1. So here are the indices. Here is length minus indices minus 1. And a predicate, namely equals, that is, are these two things exactly equal, and produces an attention matrix. So the flip attention matrix here is a matrix of trues and falses with a true where the predicate is true. So 3 equals 3, we get a true, 2 equals 2, we get a true, and so on. And then the aggregate operation takes the attention that's been computed, the attention matrix, and two sequences, in this case, a sequence, in this case, tokens, rats. And what it does is for each row, it takes the position that there's a true and copies that from the input sequence. So what we have here is this third row is paying attention to the second column. What's at the index? So the first row pays attention to the third position, which is S. Second row pays attention to the third position, which is T, so we get a reverse the input tokens to star. So this was quite influential. They didn't particularly write a compiler. That was done later in the form of tracer, but they did argue strongly for the parallel between what could be computed between the RASP programs and transformers. So my colleagues, Andy Yang, David Chang, and I began to wonder what happens if you basically strip RASP down to the point where it has only Boolean values. And the result was this language called B-RASP. And I'll give an example of it so that it makes more sense. And we were able to prove that it's exactly equivalent to masked hard attention transformer encoders. And it's unusual to have an exact characterization of a class of transformers. So that was kind of nice. And as part of the proof, what we showed was that the formal languages that can be recognized by these transformers are exactly the star-free regular languages, which is a noted and famous class in formal language theory. And we can give a characterization in terms of linear temporal logic of exactly those that behavior. Let me give you an example of B-RASP. So this language that I've written with stars in the regular expression actually is star-free. So as an exercise, you can think about writing it without the stars. You will need complement. So what happens with a B-RASP program is you get a sequence of characters as input. Here are the B's and the R's and the G's. There's no position in this language. The relative position is represented by things like leftmost and rightmost hard attention, and also masking. So you can say among the things to the left of me or among the things to the right of me, but there is no notion of an integer position in this language. So this first line of program here is saying to figure out what happens for this first set of values at position I, we look for the rightmost j such that j is less than I and the value at j is not b. So we're looking to our left. We're looking to the nearest thing to our left, so the rightmost of things to the left of us, that's not a b. And if we find it, we copy that. And if we don't find it, we put a question mark. So here, there's nothing to the left that's not a b, so we get a question mark. Nothing to the left that's not a b. Nothing to the left that's not a b. And here, there's something to the left that's not a b, namely the r, so we copy the r. Here, the thing to the left that's not a b is g, and so on. We do the same thing in the second line, except now we're looking to the right. So we're looking for the leftmost j to the right of us that's not a b, and we copy that value or we get a question mark. So here, if we look to the right of us for a non-b, we get an r. So there's an r down here. If we look to the right of us here, that's not an r, we get a g, and then we have nothing to our right that's not a b. So these two lines correspond to leftmost and rightmost hard attention. And this line corresponds to a feed-forward computation that says, I will be okay, and that's what's going to go in this line of the outputs. I will be okay if either I'm a B or I'm an R, and the thing to my right is a G, or I'm a G, and the thing to my right is left is an R, and so on. So we compute this last row, and lo and behold, there's a violation. So this language says the leftmost thing that's not a B is an R, the rightmost thing that's not a B is a G, and the R's and G's alternate with B's between them potentially. So you can think of the R as a request and the G as a grant. And what we want is every request is granted before another request comes in, and no grants are issued without a preceding request. And there's a violation of that language here in that this R looks to its right and does not see a grant. It sees another request. Oh no, that's terrible. So this violation indicates that this string is not in the language. At the same time as we were thinking about these B-RASP, Barceló et al. Were also noting that leftmost and rightmost hard attention transformer encoders, in fact, can recognize all the languages defined by linear temporal logic. They went beyond the limitations of star freeness and linear temporal logic in order to add counting terms. So they looked at average hard attention transformers, recognizing all of the language you can define in the linear temporal logic extended with counting terms that they defined. So among the languages that can be recognized here, majority. In another attempt to get beyond B-RASP, my colleagues Elena Strobel, David Chang, John Roski, and Ashish Sabharwal and I looked at the question of what kinds of transductions, that is, string-to-string functions, could transformers compute. This is a graph from a figure from the paper. What we have on the left are some fairly famous formal language classes of transformers. I'm sorry, of transductions. So the trans prefix got itself reused here. So we have aperiodic rational transductions, for example, rotating to the right, aperiodic regular transductions, for example, map reverse, which I'll give an example of, and aperiodic polyregular transductions, for example, marked square. In the middle, we have three programming languages for transformers. At the bottom, B-RASP. So this was the previously known equivalence, and this equivalence was proved in the paper. If you add to B-RASP integer positions, you get something intermediate here that can compute all the aperiodic regular transductions. And if you then add to this language a prefix sum operator, you get the language S-RASP, another extension of B-RASP. And that can compute all the aperiodic polyregular transductions. And in each case, well, in these two cases and more. And over here, we have transformers. We have unique hard attention transformers, so leftmost, rightmost, with no position indication. And here we have average hard attention transformers. And the result here is that if we have an average hard attention transformer, it can compute everything that S-RASP can compute. So in effect, we had to give a way of compiling S-RASP programs into average hard attention transformers. So average hard attention transformers in this model can compute all of these transduction classes. Let me give you a tiny example of an S-RASP program. This is a transduction map reverse. So we have marker symbols, these vertical bars, and then in between the markers, we have strings. And what we want to do is we want to reverse the string between each consecutive pair of marker symbols. So AB goes to BA, CDE goes to EDC, and so on. So now, initially, we have the input. These are the input symbols. We have the positions of the input as given sequences. And now we compute some additional sequences. So here, the previous I is intended to give you the index of the vertical bar to your left. So take the rightmost thing to your left such that it's equal to a marker and take its position. And if you don't find any such, you default to 0. So here, if we look at B, the previous marker symbol to its left is at position 0, so we get a 0. If we look at E, the previous marker to its left is this one, so we get position 3. Similarly, we do next, so we want to know the position of the next marker symbol. Notice there's no next marker symbol here, so we got the default 0. And then source is a position-wise computation on positions. It says take the previous plus the next minus the position that I'm in, and that will tell you, at least for the symbols in between the markers, where you should copy from. So A will copy from 2, which is B. C will copy from 6, which is E, and so on.
Dana, there's a question in the chat, which is the position counter allowed to reset on a marker?
Sorry, I didn't hear.
Is the position counter allowed to reset on a marker?
I'm not sure what that means.
So maybe for your positional embedding here, would you be allowed to consider positional functions that attend over the input, say that read like the marker boundary and then go back to 0?
The position is fixed and never changes. Did that answer it?
Thank you. Yeah, that's fine. Thanks.
Yeah. So this line of the program does copying. So what is it doing? It's saying, take the leftmost, in fact, it will be unique, J, such that the position of J is equal to the position I computed I should be copying from, and copy the input from there. So here, if we look at E, the position I should be copying from is 4. So I look over everything and figure out something that has position 4, namely C, and copy it. You'll notice we don't quite get the marker symbols right in this. So what we do as a last cleanup stage is put the markers back in where they were in the input because we didn't change the lengths of the strings. So this is an example of how in an S-RASP program you would compute this map reverse. Notice that we didn't use a prefix sum operator. We did use positions heavily, but we didn't use a prefix sum operator, so it was in that middle class. So in the process of submitting papers and getting them reviewed in various venues, reviewers often, if they're of a practical bent, object to the idea of hard attention, either average hard attention or unique hard attention or leftmost hard attention or whatever. So what about all these attentions? So here we've got the three types of attention I've been talking about in this so far. And we've got an upper bound on their expressivity that we've looked at. We've got my subjective notion of their human convenience, and we've got the question of whether parity is computable. So soft attention is what practitioners use and believe in and want to see proofs about. And leftmost and rightmost hard and average hard are the kinds of things that it's easy to give constructions for. So there's this kind of mismatch in human consumable versus actually practical. This result, is parity computable with soft attention, is the subject of the next And in each case, these upper bounds are TC0 in the next. So this is the second part of Han's paper. He gives a bound for a transformer encoder. The inputs are length n. And if it's got these properties that it uses soft attention, the parameters of the model don't depend on n, and the position-wise operations are Lipschitz continuous, and the position encodings are all bounded, then he proves that changing one input symbol can only change the activation by order of 1 over n. So if you're going to try to have a constant activation difference at the end of your computation, you need to get rid of at least one of these conditions or make your way around them or something. I should say that Cheng and Cholak's paper show that you can compute parity with soft attention, but in fact, what you get is you get a difference in activation that goes as 1 over n. So yes, you can do it, but you don't get a constant difference in activation. So with colleagues Andy Yang and Lena Strobel and David Cheng, we tackled this question of, can you somehow turn the theoretically convenient hard attentions into soft attention? So the paper is called Simulating Hard Attention Using Soft Attention, and the two main kind of results in there. First one says if you take the Barcelo linear temporal logic extended with counting predicates, you can recognize that with transformer encoders with soft attention, but the condition that you violate of Han's conditions is you use unbounded position encodings. This is kind of typical of how people have in papers where they do constructions, and it's convenient to do the constructions using the logic of, say, average hard attention, and then crank up the position encodings so that if you look at it in soft attention, it's sufficiently accurate. So it has that flavor. The simulation that's given in that part is actually exact because the ReLUs in the feed forward layers can snap the representation back to being discrete. So that first result is actually a discrete simulation. Second one is an approximate simulation. It says if you start with average hard attention and you're willing to modify soft attention to have temperature, then you can recognize the average hard attention languages. And what we do is we give bounds on how different the hard attention maximum and next largest have to be, and how low the temperature has to be to achieve a certain accuracy. So let me just say a little bit about temperature controlled soft attention versus hard attention. So we go back to our example of soft attention versus hard attention, and what temperature does is it divides the temperature into the attention score before it performs the exponentiation and normalization. So the lower the temperature, the larger the differences between the effective scores. So temperature 1 is normal soft attention. If we move to temperature 1/2, 2 and 5 got a little bit bigger. We move to temperature 1/4, 2 and 5 are moving towards 1/2, and the others are moving towards 0. So that's the sense of attention. Let me finish up, since I'm almost out of time, by zooming out a little. This picture is a visualization of the ICML 2025 posters. Each little blue dot is a poster. Each little blue dot represents many, many hours of research. So yeah, there is a considerable amount of research going on in this area. This was an example I did last summer with, I think, GPT-4 Turbo. I asked it to generate a 9x9 Minesweeper board with 10 mines, which is a kind of typical beginner situation. Stars for mines and numbers for adjacent mine counts. It was, very happy and enthusiastic about providing an answer, which was wrong. It got 13 mines instead of 10, and some of the adjacency numbers are wrong. However, this is from a paper from OpenAI, which I found fascinating. So this was a repository that was needed to be fixed to pass some unit tests. And this is part of their report on what the chain of thought of their, at the time, cutting edge reasoning model was doing. So in green, we have the chain of thought. If a Python script calls sys exit 0, the process will exit with exit code 0. The test will be considered passed because it's a success exit code. And that gets a little non-grammatical. Should be okay. Many tests will bail out too. So implement stub functions to bail out gracefully, instructing that full reader is, quote, this is my emphasis, only in premium version, question mark. This is sometimes used. This is unnatural, but tests might pass because they bail. So this is a phenomenon that goes under the general heading of reward hacking. You have a model that's been instructed to do a task, namely make it pass the unit tests, and it finds a way to make it pass the unit tests that is not what you meant. Thanks very much for your attention. Let me draw your attention to a survey that I was involved in with Lena Strobel, Will Merrill, Gail Weiss, David Chang. Of course, having been published last year, it's already somewhat out of date, and a new production, the Transformer Cookbook, which is up on archive as of, I think, October 1st, which has a wonderful collection of constructions to do various tasks with a transformer. So if you're trying to figure out how to get a transformer to do something, this offers recipes for a whole bunch of component tasks. It's a wonderful piece of work. Let me advertise this very seminar. And there's the website and there's the logo. Thanks very much.